Yes, on a multi-grounded system, the primary and secondary neutral should be interconnected according to National Electrical Safety Code rules. This interconnection is a fundamental aspect of multi-grounded neutral systems and serves several critical purposes. It's important to understand the structure of a multi-grounded neutral system to appreciate the significance of this interconnection. A multi-grounded neutral system involves grounding the neutral conductor at multiple points along its length. These grounding points are typically located at each transformer and at regular intervals along the distribution lines. The primary side of the transformer refers to the high voltage side, which is connected to the distribution network, while the secondary side is the low voltage side that feeds power to consumers. Interconnecting the primary and secondary neutrals means establishing a continuous, low impedance path between the neutral conductors on both sides of the distribution transformer. This connection is typically made at the transformer location itself. There are several key reasons why this interconnection is required. Firstly, voltage stabilization. The interconnection of the primary and secondary neutrals helps to stabilize the voltage on the secondary side of the transformer. By providing a direct connection to the multi-grounded primary neutral, the secondary neutral is effectively tied to the same reference potential. This minimizes voltage fluctuations and imbalances on the secondary side, ensuring a more stable and reliable power supply for consumers. Secondly, fault current path. In the event of a ground fault on either the primary or secondary side of the transformer, the interconnected neutral provides a low impedance path for fault current to flow back to the source. This is crucial for the rapid operation of overcurrent protection devices, such as fuses and circuit breakers, which are designed to interrupt the flow of fault current and prevent damage to equipment and hazards to personnel. Without a properly interconnected neutral, the fault current path may be significantly higher impedance, which can delay the operation of protective devices and increase the risk of damage or injury. Thirdly, reduction of ground potential rise. During a ground fault, the flow of fault current through the earth can cause a localized rise in ground potential. This is known as ground potential rise, or GPR. If the primary and secondary neutrals are not interconnected, the ground potential rise on the primary side can be transferred to the secondary side, potentially exposing consumers to dangerous voltage levels. By interconnecting the neutrals, the ground potential rise is effectively mitigated, as the interconnected neutral provides a low impedance path for fault current to return to the source, minimizing the voltage difference between the local ground and the neutral conductor. Fourthly, minimization of neutral to earth voltage. In a properly designed and maintained multi-grounded neutral system, the voltage between the neutral conductor and the earth should be close to 0 volts. This is because the multiple grounding points along the neutral conductor help to equalize the potential between the neutral and the earth. However, if the primary and secondary neutrals are not interconnected, the neutral to earth voltage on the secondary side can be significantly higher, potentially causing nuisance tripping of ground fault circuit interrupters and other sensitive electronic equipment. The interconnection of the neutrals helps to minimize the neutral to earth voltage, ensuring proper operation of these devices. The National Electrical Safety Code, or NESC, provides specific requirements for the design and installation of multi-grounded neutral systems, including the interconnection of primary and secondary neutrals. These requirements are intended to ensure the safety and reliability of the electrical distribution system. It is essential to consult the NESC and other relevant standards to ensure that the interconnection of neutrals is performed correctly and in accordance with all applicable regulations. The specific requirements for interconnecting primary and secondary neutrals can vary depending on the voltage level, system configuration, and local regulation. However, some general guidelines can be provided. Firstly, the interconnection should be made at the transformer location. The connection between the primary and secondary neutral should be made at the transformer location, typically within the transformer enclosure or at a nearby grounding point. Secondly, the connection should be made with a properly sized conductor. The conductor used to interconnect the neutral should be sized according to the applicable standards and regulations. It should be capable of carrying the maximum expected fault current without overheating or becoming damaged. Thirdly, the connection should be made with a low impedance connection. The connection between the neutral should be made with a low impedance connection to minimize voltage drop and ensure proper operation of protective devices. This can be achieved by using properly sized conductors and making secure, corrosion-resistant connections. Fourthly, the connection should be made in accordance with all applicable codes and standards. The interconnection of neutral should be performed in accordance with all applicable codes and standards, including the National Electrical Safety Code, the National Electrical Code, and any local regulations. It is essential to consult these documents and follow all applicable requirements to ensure a safe and reliable installation. In addition to the above guidelines, it is also important to consider the following factors when interconnecting primary and secondary neutrals. Firstly, coordination with grounding electrodes. The interconnection of neutrals should be coordinated with the grounding electrodes on both the primary and secondary sides of the transformer. The grounding electrodes should be properly sized and installed to provide a low impedance path to ground for fault current. Secondly, surge protection. Surge protection devices should be installed on both the primary and secondary sides of the transformer to protect against voltage surges caused by lightning or switching events. The surge protection devices should be properly grounded to provide a low impedance path for surge current to flow to ground. Thirdly, communication with the utility. It is essential to communicate with the local utility company before interconnecting primary and secondary neutrals. The utility may have specific requirements or guidelines that must be followed to ensure the safety and reliability of the electrical distribution system. Fourthly, regular inspection and maintenance. The interconnection of neutral should be regularly inspected and maintained to ensure that it is in good condition and functioning properly. This includes checking the condition of the conductors, connections, and grounding electrodes, and making any necessary repairs or replacements. It is important to note that the interconnection of primary and secondary neutrals is not always required. In some cases, it may be permissible to isolate the secondary neutral from the primary neutral. However, this is typically only done in special circumstances, such as when the secondary system is a separately derived system or when there are specific concerns about ground current flow. In these cases, it is essential to consult with a qualified electrical engineer and follow all applicable codes and standards to ensure that the system is properly designed and installed. In summary, the interconnection of primary and secondary neutrals is a fundamental aspect of multi-grounded neutral systems. It is required by the National Electrical Safety Code and other applicable standards to ensure the safety and reliability of the electrical distribution system. The interconnection helps to stabilize voltage, provide a low impedance path for fault current, reduce ground potential rise, and minimize neutral to earth voltage. It is essential to follow all applicable codes and standards and consult with a qualified electrical engineer when interconnecting primary and secondary neutrals. The benefits of interconnecting primary and secondary neutrals in multi-grounded systems are substantial and contribute significantly to the overall safety and reliability of electrical power distribution. Firstly, enhanced safety is provided. The interconnection creates a robust, low impedance path for fault current, enabling rapid operation of protective devices like circuit breakers and fuses. This minimizes the duration of fault conditions, reducing the risk of electrical shock and fire hazards. Secondly, improved voltage stability is observed. By tying the secondary neutral to the multi-grounded primary neutral, voltage fluctuations and imbalances on the secondary side are minimized. This ensures a more stable and reliable power supply for consumers, preventing damage to sensitive electronic equipment. Thirdly, effective ground potential rise mitigation is achieved. Interconnecting the neutrals minimizes the ground potential rise during fault conditions, preventing dangerous voltage levels from being transferred to the secondary side and protecting consumers from potential hazards. Fourthly, minimized neutral to earth voltage is maintained. The interconnection helps maintain a low neutral to earth voltage, preventing nuisance tripping of ground fault circuit interrupters, or GFCIs, and ensuring proper operation of sensitive electronic equipment. Fifthly, compliance with standards is met. Interconnecting primary and secondary neutrals ensures compliance with the National Electrical Safety Code, or NESC, and other relevant standards which are designed to promote safety and reliability in electrical systems. Sixthly, enhanced system resilience is observed. The interconnected neutral provides a more robust and resilient system capable of withstanding fault conditions and maintaining a stable power supply. Now let's consider potential challenges and considerations when implementing this interconnection. Firstly, coordination with existing grounding systems is required. The interconnection should be carefully coordinated with existing grounding systems to avoid creating unintended ground loops or circulating currents. Secondly, proper conductor sizing must be ensured. The conductor used to interconnect the neutrals must be properly sized to handle the maximum expected fault current without overheating or becoming damaged. Thirdly, secure and corrosion-resistant connections are critical. Connections must be secure and corrosion-resistant to ensure a reliable, low-impedance path for fault currents. Fourthly, surge protection devices are needed. Surge protection devices should be installed to protect against voltage surges caused by lightning or switching events. Fifthly, regular inspection and maintenance are essential. Regular inspection and maintenance are necessary to ensure that the interconnection remains in good condition and functioning properly. Sixthly, coordination with the utility company is important. Close coordination with the local utility company is essential to ensure that the interconnection meets their requirements and does not negatively impact the overall distribution system. To further illustrate the importance of this interconnection, consider a scenario where a ground fault occurs on the primary side of a distribution transformer. If the primary and secondary neutrals are not interconnected, the fault current may have to travel through a higher impedance path, such as the earth, to return to the source. This can result in a slow response time for protective devices and a higher ground potential rise, increasing the risk of electrical shock. In contrast, with an interconnected neutral, the fault current has a low impedance path to return to the source, enabling rapid operation of protective devices and minimizing the ground potential rise. This significantly enhances safety and reduces the risk of damage. Another important consideration is the impact of distributed generation, such as solar panels, on multi-grounded neutral systems. Distributed generation can introduce additional complexities to the design and operation of these systems, and it is important to ensure that the interconnection of neutrals is properly coordinated with the distributed generation equipment. In some cases, it may be necessary to install additional grounding electrodes or other measures to mitigate the potential impact of distributed generation on the grounding system. The interconnection of primary and secondary neutrals is a critical aspect of multi-grounded neutral systems that requires careful planning, design, and implementation. By following the guidelines and requirements outlined in the National Electrical Safety Code and other relevant standards, it is possible to ensure a safe, reliable, and efficient electrical power distribution system. In conclusion, interconnecting the primary and secondary neutrals in a multi-grounded system is not just a recommendation, it is a requirement based on established safety standards and engineering principles. This practice ensures proper voltage stabilization, provides a reliable fault current path, reduces ground potential rise, and minimizes neutral to earth voltage, all of which contribute to a safer and more reliable electrical system. Ignoring this interconnection can lead to increased risks of electrical shock, equipment damage, and system instability. Therefore, adherence to the NESC and other relevant standards is crucial for anyone involved in the design, installation, or maintenance of multi-grounded neutral systems. This interconnection is a cornerstone of electrical safety and system performance.